Okay, so before we begin, it is best if we can look back what we have learned so far, I think starting from yesterday. So yesterday we have gone through several examples for elastic and also plastic deformation based on, I think, some situation. Okay, some examples with regards to the formula of calculating stress, modulus of elasticity or strain, provided with different types of value in the questions. We also have looked or understand what does it mean by yield strength, or offset, plastic offset, plastic strain. Okay, and we also have looked through several examples. For example, like this one. Okay, remember that whenever you wanted to calculate or identify the ultimate tensile strength or maybe the maximum tensile of an object, it is best to read through the optimum value from the profile of stress to strain curve. So this could give you a guide in order to calculate another values. Modulus of elasticity or Young modulus can be calculated in the linear region from the gradient. Okay, identifying the linear region, and after that calculating the gradient will give you the Young modulus or modulus of elasticity value. And other than that, yield strength. Okay, if let's say that you are given an offset value, you can read through the yield strength by just drawing a line that is perpendicular to this curve until it overlaps with your I think curve. This overlap actually means that it start to become plastic. It's not going to be linear. Then this will be your yield strength. Okay. So other than that, we also have looked through other examples, and we also have learned about ductility. So ductility can be calculated based on the percentage of elongation and also reduced in area. So from these two values, you can identify whether the object or the material is ductile or less ductile. This is actually looking at the value. Ductile and the brittle fracture, very ductile samples like plastic and others will have, I think, quite a sharp fracture ends. Meanwhile, for brittle sample, it's going to be flat or mostly like crack. And we also have looked through these examples in order to see whether the materials ductile or less ductile. So in this case, from the value for percentage of elongation and percent of reduce in area is quite small, so it's less ductile. Okay, so I'm giving one example of this. Okay, so you have a different types of metals, different types of metals alloy, and then after that, it has a different stress to strain profile. Okay, so basically, looking at this diagram or this figure, what can you actually indicate? I just want a frank maybe answer or opinion from you guys. Nathan nak start pagi-pagi ni. Just want to ask. Christine Rintau Engkiao. Christine, are you there? Christine. No, she's not there. Okay, siapa ni? Hasnun. Hasnun Yusuf. Hasnun, are you there?
Yes, doctor.
Okay, Hasnun. So what can you actually maybe elaborate from this figure? What can you actually discuss? What can you see? You have different types of material. You have steel, you have brass, you have copper, nail, you have aluminium alloys. So what can you actually indicate? Apa-apa je lah yang you boleh nampak. Maybe yang paling
Hardness.
tinggi, hardness. How did you measure hardness? How did you say a material is actually hard? By looking at what?
Apply a stress on the metal.
Okay, understood. But from this figure, how can you actually identify? Kalau macam contoh saya tanya, if I ask you, which one of this one is considered to be the hardest material? Macam mana kita nak jawab? Kalau kita nak tahu dia ni hardest or not? Any idea? Hasnul?
Uh,
No idea.
not sure.
It's okay. It's okay. At least you are trying. Okay. So Hasnul actually pointed out one key things, which is on the hardness. I have to agree. From this figure, we can actually look or maybe indicate which one is the hardest. Okay. So when I ask, how do we determine whether the material will be the hardest or the strongest material? Okay. So Hasnul tak dapat nak bantu. Okay. How about I ask another person? Nik Muhammad Syafiq. Nik Muhammad Syafiq ada tak?
Yes, Doctor.
Okay. Tak apa, jangan tak takut. Okay. Just nak sembang je. Alright. So, Nik, daripada figure ni, macam mana kita nak tahu? I mean, the material is actually the hardest. By looking at what?
Uh, I'm not sure, Doctor.
Not sure. Okay. Tak apa, Nik. Terima kasihlah kerana cuba untuk menjawab juga walaupun tak tahu. Alright. Saya tanya satu orang lagi lah. Last. Oh, okay. Nur Khairin Camelia binti Abdul Muain. Khairin Camelia. Sedap nama ni. Ada tak ada? Khairin.
Yes, Doctor.
Okay, alright. There. So, Khairin, how can we identify which material is basically the hardest? Soalan yang sama. Same question.
Maybe by looking at the stress.
Stress.
I'm not sure, Doctor. Sorry.
Okay, never mind. Close enough, but okay. Basically, if we want to identify which one is the hardest, is when you look at the profile and if, let's say that the linear region is the longest. So, taking from that statement, which one do you think will be the hardest from all of this? Okay. Kita tanya juga orang lain. Tadi saya dah bagi jawapan dah. Saya cakap, I think I told you, in order to identify which one is the hardest, is by looking at the longest linear. Linear yang paling besar. Linear yang paling panjang. Okay. So, saya malah nak tanya orang yang sama je. No Syahira. No Syahira, ada tak? No Syahira binti Syahar. No Syahira. Tak ada. Nur Nadia. Nur Nadia Maznan. Nadia ada tak Nadia?
Yes, Doctor.
Okay, Nadia. So which one do you think that is the hardest? Taking from my own statement, which I have explained earlier. So which one? Which one do you think is the hardest?
Stainless steel.
Which stainless steel? Dia ada stainless steel yang lain juga ni.
The higher one.
Oh, 304. Okay. All right. Fair enough. Thank you, Nadia. Maybe another one, another person. Siapa I nak tanya ni? Sin Yong Ong. Sin Yong Ong. Are you there?
Yes, Doctor.
Okay. All right. So, I think earlier Nadia told us that 304 stainless steel is the highest. So, I mean, having the highest hardness. Are you agree with this, or you have another answer?
I think it's 1,100 for aluminium.
1,100 for aluminium. 1,100 aluminium.
The lowest one.
Lowest.
1,100 for aluminium.
Oh, this one. Okay, this one.
No.
I talking about
1,100 for aluminium.
1,100. Oh, this one. Is it this one?
Yeah.
Are you saying this one? Okay.
Yes.
All right. Okay. So thank you for your answer. Well, basically, the answer that we are looking at is, as I said, in order to find the hardness or the hardest material is by looking at the more elastic properties. Okay. So if you want to indicate the more elastic properties, then it should reflect to the linear region. So any linear region that produce, okay, maybe quite sharp or maybe quite long, linear, then this can be indicated as hardness. Okay. So maybe we'll look through this answer. 1,100 O aluminium. Okay. Basically, if we look through this sample from zero, from origin, it start to go up, and after that it goes bending. So if you notice, this is a bending, and then after that it goes gradually up again. Okay. So do you think that this material already experienced plastic deformation or no? The answer is actually yes, because this material have already forming a bending. As I said, anything that produce bending will actually indicate that it already produced plastic deformation. Okay, right. So what about stainless steel 304? So meaning that this material is not the hardest one. At least, I mean, well, basically it's the least hardest, right? So 304 stainless steel. Okay. So if we check from this plot, even when it starts, it already gives like, a stress value of maybe 50 something. It goes up, up until here. The offset, the offset is around 0.4 something. Okay. And if you compare, this is actually among the highest in terms of offset value. Okay. Tak ada yang lain. Yang lain semua offset starting from even lower value. So 304 stainless steel have one of the highest, okay, offset value. So when you have highest offset value, then it means that the plastic deformation occurs later, right? Meaning that this material is quite elastic initially, and then after that, then only it become plastic. So even plastic pun dia tak bending curvy, dia jadi macam bengkok, bend a bit saja. Right. So the answer is actually stainless steel 304 lah. This is actually one of the hardest material. So at least you know when you have this kind of data, okay, this material is actually the hardest material. Right. So other than that, you can also calculate the other things, modulus of elasticity, ultimate tensile stress, and yield offsets, yield strength from offsets value. And today we are going to continue with toughness. Just a few remaining part. Toughness, hard and toughness. What does it mean by hard and what does it mean by tough? Satu keras, satu lagi kita cakap padu lah in Malay. Tough and hard. So energy requires to break a unit volume of a material. So this is actually defined by toughness. Approximate by the area under the stress strain curve. Okay. So this material, if you want to indicate which one is the toughest, is actually by looking at the area underneath the curve. So if the area is bigger, then we'll say that the material is tough. Okay. So brittle material normally have a very small toughness. Okay, because after certain value, it start to break. Dia patah terus. Okay. Metals, it has a larger toughness because if you see from the curve, okay, when it become elastic, plastic, it still can withstand the force. Okay, so dia tak fracture until certain time, then only it fracture. Okay, so this actually having quite, I think, higher value of area underneath the curve, then this can be considered larger. And finally, if you have unreinforced polymer, so a very slow elastic, and then after that plastic, and then after that maintain. So this is very small toughness. So it's not as tough as compared to. Okay, so brittle fracture normally indicating elastic energy, and ductile fracture actually indicates the combination between plastic and also elastic energy. Resilience. Okay, so resilience is the ability of a material to store energy. So what would be the examples of resilient material? Okay, the simplest one is spring lah. So spring, when you pull it, okay, so what happens is that the spring will absorb, okay, the energy, the amount of energy that is being applied, and then after that, when you release the spring, what happened? It will automatically goes back into its original shape. So how actually the spring can goes back quite fast? Because it able to store the energy applied before that. Okay? So the energy stored best strain. If we simplify, if we assume a linear stress strain curve to this, it will simplify to UR is equals to half sigma y and epsilon y. Okay, but nevertheless, as what I told you, this is also part of the things that we introduce it for just for your information. It is not something for you guys to really understand. At least we know. And finally, we are talking about hardness. I think before this, we have talked about hardness and everything. Okay, but how do we measure hardness in reality? Apart from using ultimate tensile stress machine, we can actually measure hardness using hardness machine. To measure hardness, okay, is basically to measure the resistance of a material to penetrate by a sharp object. So you will have a material and then you will put some indenter, some object, a very sharp object, okay, on top, and then after that you apply force. So if the material is quite hard, then what will happen is that the sharp object is very difficult to penetrate. Okay, if it is like rubber, plastic, you can see that it goes, it penetrates, okay, and it needs certain time to go through. Okay, brittle object, it will not going to penetrate, but until certain amount of force, what happen is it will crack and break. Okay, so this is actually how we are going to measure hardness. Theoretically, resistance to permanently indenting the surface. Large hardness means that resistance to plastic deformation or cracking in compression. So as what I've told you earlier, okay, the hardest material is actually having higher elastic. So it means that it has a resistance to plastic deformation. If we look to the previous examples over here, okay, why SS stainless steel 304 is the hardest is because it has quite huge amount of elastic range before it become plastic, right? So kalau dia memang betul linear saja naik macam tu without any bending or what, then that is actually the hardest material. Normally hardest material will be for little sample lah. Okay. And you can see from here the examples. Plastic have very least hardness. Aluminium alloys, brushes will have least. Okay, and going up, okay, steel, cutting tools, nitride steels, diamond, all these are actually going to have a very high value of hardness. So this is actually one of the indenter. So we have different shape of indenter. You have a round shape, bentuk macam bola, spherical. You have also very sharp edge of indenter. So what happened is that if this indenter being applied with certain force, 1 to 1,000 gram of force, and if you actually remove or unload the material, you will calculate what will be the indent area over here. So the less the indent, or if there's no indent, that means that it has a larger hardness. Okay. So for hardness test, it is actually to measure the resistance of material to penetration by a sharp object. So we have a macro hardness that normally uses load that is more than 2 Newton. Micro hardness will use, I think, load that is less than 2 Newton. And nano hardness that use less than, I think, less than 1, normally around 100 micronewton, very small. So what actually makes the difference? It's depending on the types of material that you are focusing. For examples, for macro hardness, all these are actually used for bigger objects like metals, okay, ceramics, rocks, minerals, and etc. Micro, okay, normally will be used for polymer any thin material. This may be bulky or big material. Is for thin material, okay, polymers, for example. And then you have nano hardness. So nano hardness normally for coatings, any thin layer like coatings, paint, and whatsoever. So you will use nano hardness. Okay. Right, so we have different examples for macro hardness. For example, Rockwell test. Okay, so for Rockwell test, minimum load will be around 10 kilo, and major load will be even higher, 60, 100, 150, and whatsoever. Okay, we also have a so-called Brinell test. Okay, so Brinell hardness test, it has a different load as well. But what makes the difference between Rockwell and also Brinell test is the type of indenter that they use. Okay, so you will see what's the difference between Rockwell and Brinell. So for Brinell, normally it will use a steel spherical indenter. Okay. Meanwhile, for Rockwell, okay, for N scale, it will use a sharp edge diamond coat. And for scale T, it will use round indenter, but the shape of indenter is not the same. We also have a different types of macro hardness, which is Vickers test. So Vickers also use diamond indenter with a fixed dimension. Like this one is 120 angle, okay, for Rockwell. And also there's knob hardness test. So knob hardness test, it use a pyramid shaped diamond with an angle of 170 angle. So theoretically is the same. It's just that the types of indenter is different. And why they use different types of indenter? Because they want to penetrate through. So it all depends on the type of materials that you are studying. The best is if you want to study, you can try with the least one, maybe the standard one. You can use Rockwell, and then after that, if let's say that the material have a very huge variation in terms of the percent area error, then you can try with Brinell, knob, or also Vickers. All right, so as a comparison, this is actually what I told you. For the hardness testing techniques, the types of indenter makes the difference, because it will actually give you a different hardness number and I think results. So for Brinell, it used 10 millimeter steel spherical carbon or carbon tungsten carbide indenter. Vickers micro hardness use diamond pyramid with area or maybe theta angle of 136. Not micro hardness areas like is quite big. And I think for Rockwell and superficial Rockwell it has like two type, N and T. So you can have like 120 diamond cone or spherical, I think indenter. Okay, so once you get the results, you can actually maybe, or before that, in order to choose the right test, we have to look at what types of load that you want to put. So if the material is quite thin, if it's thick, then different types of load that you are going to apply. So all this actually need to follow standard STM methods, okay, with a different types of indenter. So some suggestion, if you want to do tests with different types of metals, you can use Rockwell with a different indenter, diamond, diamond cone, steel ball, and others. So this is actually the comparison of hardness scale. So to identify which one is basically the hardness, okay, the hardest. Okay, so you can actually see from the scale. From here, we know that plastic will have a very low scale for hardness. Okay. Meanwhile, for steel or metal, diamond will have a higher hardness scale. Right. So as a summary for this topic, what we have learned so far is basically on mechanical properties. We have been introduced to the definition of stress and also strain. Okay. And we also have looked through the examples of elastic behavior and plastic behavior. Toughness, ductility, hardness, we also have addressed it quite well. And I believe this actually marks the end of this chapter. So just want to ask you guys if you have any questions or anything that you want to raise before we go into the next chapter. Anything? Any question? Right.